Hi everyone, this is Professor Majumdar and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show finite element analysis of an overhanging beam with a combination of uniformly distributed load and also concentrated point load. Let us see the statement of the problem. Using ANSYS mechanical ABDL, draw the shear force and bending moment diagram of the following beam and compare the results. So the problem is stating that it is having one overhanging beam with a total span of 6 meter and support is provided at B from left hand side at distance of 1 meter, and another support is provided at the extreme right hand side, and we are providing a point concentrated load of 60 kilonewton at A and uniformly distributed load of 60 kilonewton per meter from B to C, and we are providing another moment at D at the rate of 120 kilonewton meter. It is in the clockwise direction, so it will be negative, right? So without wasting time, let us start our analysis using ANSYS mechanical ABDL, right? First of all, we need to create a directory and we need to save everything in that directory. Next to that, we need to change the title of this one. We can do it from File, Change Title. We are keeping the name of this one as FA7. Okay. To see the title, plot to replot, it will show the title at the lower left corner, right? Next to that, we need to select what type of analysis it is. It is definitely one static structural analysis. So preferences, we are keeping structural analysis checked in. Okay, done. Now we need to provide elemental properties. It will come from preprocessor. Element type, add, edit, delete. We need to add it. So we are considering beam with 3D finite strain and element type reference number is 1. Okay. Now from options, we are selecting element behavior as cubic form. Okay. Let's close it. Now we need to provide material properties, material models, structural, linear, elastic and isotropic. Isotropic means material property remains same in all directions, and modulus of elasticity is 2 into 10 to the 11 Newton per meter square, and Poisson's ratio is 0.3, right? So modulus of elasticity 2e11 and Poisson's ratio is 0.3. Okay, done. Let us close it. Now sections, beam cone sections. It is a square cross section of breadth equal to 0.01 meter and height is equal to 0.01 meter. So we are applying breadth equal to 0.01 meter and height also 0.01 meter. Okay, done. Next to that, we need to start our modeling, and better to create key points. So starting with key points in active coordinate system, first key point will be created at origin, so apply. Second one will be at a distance of 1 meter from origin, apply. Third key point will be at a distance of 4 meter from origin, apply. Fourth one will be at a distance of 5 meter from origin, apply. And fifth one will be at a distance of 6 meter from origin, apply. And for orientation of the beam, we need to provide another key point. Let us provide that key point to be situated at a distance of x equal to 0 and y equal to -4. Okay, we created all the key points. Now these key points to be joined in the form of lines, right? So lines, straight line, let us join key point 1 and 2. Next one, it will be key point 2 and 3, 3 and 4, and finally 4 and 5. We joined all the lines. Okay, next to that, we need to start meshing, and it will start from mesh attributes. We need to select that extra key point 6 that is required for orientation of the beam. So select all lines and orientation of the key point should be taken into consideration. Okay, so let us select that key point 6 for orientation. Okay, done. Now we need to start meshing from size controls, and we are considering manual size with lines. Let us select all lines and keeping the number of elemental divisions for each line is equal to 10 divisions. Okay, now finally we can mesh it. Mesh lines, pick all the lines are selected and meshed, right? Meshing is complete. Now we need to apply our boundary conditions from loads. Loads analysis type, it is a new analysis and it is definitely a static structural analysis. Now we need to define loads. Loads apply structural displacement on key points. Now to see the specific locations, you can select lines from plot lines, and we know that we need to put supports at specific locations. This one will be fixed and this one will be having some kind of support. This point and this point will be having two different supports. Let us select the extreme right hand side, apply. It will be restricted to move along x, y, z, and its rotation is also restricted along x and y. It is only allowed to rotate along z. Apply. Now select the next point here. Okay, again this one will be restricted to move along y and z, and its rotation is also restricted along x and y. It is allowed to rotate along z, and also it is allowed to translate along x. Okay, done. Now we need to apply a force of 60 kilonewton at this location. So structural force moment on key points, let us select the first location here, apply. It will be in the y direction downwards, so it will be minus 60,000 Newton. Apply. Next one, another moment to be applied at this location, so select that specific location. Okay, it will be moment along z, that is mz, and as moment is applied in a clockwise direction, so it will be minus 120 kilonewton meter moment is applied at this location, and the direction is actually negative as it is applied along clockwise direction, right? Okay, moment is applied. Now the last one, we need to apply uniformly distributed load of 40 kilonewton per meter with a span from here to here, right? So you can apply pressure on beams, right? And you can select the specific nodes from box. Okay, and it will be ranging from 40 kilonewton meter to 40 kilonewton meter. It will be same through all the points. We are starting at node I with 40,000 Newton per meter and finishing at node J with 40,000 Newton per meter, and the direction is indicated by this minus sign. It will be in the downward direction. Okay, done. We applied all the boundary conditions. Now we need to solve it. So solution, solve current LS. If everything is right, it will show solution is done. Okay, it is showing solution is done, so everything is perfect. We can see our results from general post processing. Let us close it. And general post processing, we need to read results from last set. Now we need to form element table, define table, and we know that for seeing the bending moment and shear force diagrams, we need to define on specific numbers. For bending moment, we need to select SMIS 2 and SMIS 15, and similarly for shear force, we need to select numbers SMIS 5 and SMIS 18, right? So add, and from drop down menu we can select by sequence number, and it will be SMISC 2. Apply. Repeat the process for the other node by sequence number and selecting SMISC 15. Apply. Next one, again repeat the process by sequence number. It will be SMISC 5. Apply. And the last one by sequence number and SMISC 18. Okay, we selected all the numbers. First two numbers, SMIS 2 and SMIS 15, it will represent bending moment diagram, and SMIS 5 and 18 will represent shear force diagram. Okay, let us close it. Now first of all, we want to see results from listing. So list results, and we want to see reaction solution, right? So reaction solution, and we are selecting all items. It is showing that maximum reaction is occurring at node number 2 and node number 62. At node number 2 it is 132 kilonewton, and at node number 62 it is 48 kilonewton. Let us see this one from our actual question also, whether it is okay or not. It is also showing the same thing. At location B, reaction is 132 kilonewton, and at location D it is 48 kilonewton. So what we got in our ANSYS mechanical epidel, it is exactly same, right? Next one, we want to see the bending moment and shear force together with listing. So element table data, and let us select all the numbers SMS 2 and 15 for bending moment, and SMS 5 and 18 for shear force. Okay, so this is representing shear force and bending moment at each nodes, right? We're having total 40 different nodes, and first two columns represented by SMS 2 and SMS 15 is representing the values of bending moment diagrams at specific nodes, and similarly third and fourth column represented by SMS 5 and SMS 18 is representing the values of different nodes of shear force diagram, right? And you can see here maximum bending moment is actually occurring at node number 31. It is 48,000 Newton meter, and minimum is occurring at node number 30. It is minus 72,000 Newton meter, right? Similarly, maximum shear force is occurring at node number 11. It is 72,000 Newton, and minimum is occurring at node number 1. It is 60,000 Newton, right? Let us close it. Next to that, plot results, and we'll see the bending moment and shear force diagrams. So plot results, can to plot line elemental response, and we'll see the bending moment diagram. So it will be SMS 2 and SMS 15. Okay, let us see this one. It is showing that maximum bending moment is occurring at this location. It is 48,000 Newton meter or 48 kilonewton meter, and minimum is occurring at this location. It is minus 72,000 Newton meter or minus 72 kilonewton meter. Let us see this one from our question paper also, and let us compare these things. It is also showing exactly same thing. It is showing that maximum bending moment is occurring at this location. It is 48 kilonewton meter, and minimum is at this location. It is minus 72 kilonewton meter. So it is exactly same, right? Okay. Next one, we want to see shear force diagram. So again, line elemental response, and it will be SMS 5 and SMS 18. Okay. You can see here again, maximum shear force is occurring at this location. It is 72,000 Newton or 72 kilonewton, and minimum is occurring at this location. Through the span, it is minus 60,000 Newton or minus 60 kilonewton, and we can compare this one with the question paper itself. Let us see that. It is also showing the same thing. Maximum shear force is 72 kilonewton at this location, and minimum is 60 kilonewton at this span, right? So it is exactly same. Results from ANSYS mechanical epidel is validating the results obtained from theoretical results from the question paper, right? Next to that, we want to see the displacement of each node along y directions. First of all, see in the form of listing. So list results, and it will be nodal solution, and we want to see displacement of each node. So DOF solution, y component of displacement. Okay, it is showing displacement of each node. We are having total 71 numbers of nodes, and you can see here maximum displacement is occurring at node number 1. It is minus 366.01. Okay, now we'll plot the displacement of each nodes. So plot results, nodal solution, DOF solution, and we'll see y component of displacement, right? So these are the displacement at different locations. You can see this maximum displacement is occurring at this location. It is minus 366.007, right? We can see the deform shape also from here. Let us see that deform shape, deform plus undeform. It will show the original drawing and the change drawing also. So the white one is the actually original drawing, and blue one is the change drawing. By the application of defined loads, it will be deformed in this way, right? Next to that, we want to see the animation of this beam. So first of all, we will see the beam in 3D format, right? So plot controls, style, size and shape, and display of elements should be on. Okay, so this is the beam in 3D format, right? Let us plot elements, and to see the 3D view, let us change the orientation to isometric view or oblique view. You can see this is the actual beam with a specific cross section of 0.01 meter by 0.01 meter, right? Now I want to see the animation of this beam, right? So plot controls, animate, deform results, and with the default setting we want to see translation along Y. Okay, to see translation in a better way, we can change the delay period, so this way the beam will be vibrating. Okay, let us close it. So this is all about our today's analysis. This was a very simple analysis of an overhanging beam with a combination of uniformly distributed load and also a point load. In this analysis, we have shown the shear force and bending moment diagram, and also we compared the results with the question paper itself, and the result obtained through ANSYS mechanical APDL is exactly same as given in the question paper itself. So it has validated the results obtained in the question paper, right? So with this one, we'll conclude our today's video. Thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.